To conclude today, we need to talk about converting vectors between the different coordinate systems. Everything I've done so far has been in the Cartesian, and which is also the rectangular system. And certain applications are going to require us to convert our Cartesian points and our Cartesian vectors into either the cylindrical or the spherical system. So what I'm providing you here are the methods of converting from the in between the three different systems. So if we start with either cylindrical or spherical, and we want to put those into Cartesian, these are the formulas that we'll use. So you take rho cosine phi, that gives you x if you're going from cylindrical to Cartesian. Rho sine phi gives you y if you're going from cylindrical to Cartesian. And there is no conversion necessary from cylindrical for the z to Cartesian z. Similarly, if we're going from spherical to Cartesian, you've got r sine theta cosine phi gives you x, r sine theta sine phi gives you y, and r cosine theta gives you z. So you can start in either cylindrical, you can go to Cartesian that way. Here we've got Cartesian and spherical, two cylindrical conversions. So in Cartesian, you take the square root of the x squared plus y squared, that gives you rho in cylindrical. You take the inverse tangent of y over x, that gives you phi in cylindrical. And again, no conversion between Cartesian and cylindrical is needed for the height variable. Spherical to cylindrical, r sine theta gives you rho. Phi and phi are the same, and then from spherical, r cosine theta gives you z in the cylindrical coordinate system. And then finally, well, what if we're in Cartesian and cylindrical and we want to go to spherical? To determine the radius of the sphere, you have the square root of x squared, y squared, and z squared in the Cartesian system. To determine the rotation theta along the positive z-axis, you take the inverse tangent of x squared plus y squared divided by z, which gives you the same answer as if you take the inverse cosine of z over r, where r is the radius of the sphere that you calculated up here. And then finally phi, which is the rotation as measured from the positive x-axis. It's just the inverse tangent of y over x in the Cartesian system. For cylindrical, to determine the radius of the sphere, we take the square root of rho squared and z squared. To determine theta, we take the inverse tangent of rho divided by z, and to determine phi, there is no conversion necessary. So having these charts is handy. I'm not going to give you these charts on tests, so if you want these on your note sheets, you need to put those on there yourselves. So let's do an example. Let's convert the point -5, -1, -4 into the other two systems. And indicated meters, meters, meters. That means that this is a Cartesian point. I know that because they're all in distances. There's no angles here. So let's do cylindrical conversion. So rho, as we saw from the previous three slides, is equal to x squared plus y squared. So that's equal to minus x squared plus y squared square root. So that's -5 squared plus -1 squared. So that's the square root of 26. Phi is equal to the inverse tangent of y over x. So that's equal to the inverse tangent of -1 over -5. That gives me 0.1974 radians. And z, there is no conversion necessary, so it's just -4. So what we have here is, if we were to plot the x, y, z axis here, we had -5 in the x, right there. So that's this point. I guess I should extend this line. We had -1 in the y, so So that's that point right there. And we had -4 in the z. So that is that point right there. So where do all those intersect? If I were to just extend all of those in space, and I'm trying to keep this color-coded for you. You can see I'm using red for projections on the x-axis, green for projections along the z-axis, and blue for projections on the y-axis. So that shows us where all those points intersect at, and that's kind of that coordinate right there. So that's -5, -1, -4, right? And that's in the minus octant. Right? In two-dimensional systems, we've got the first, second, third, and fourth quadrant. In three-dimensional systems, we've got 8 octants, and they're represented by what the sign of each is. Oops, I left off the 1 there. So we're in the minus octant. So in this calculation, 0.9174, this is equal to about 11.3 degrees. And so you kind of got to visualize where that is. For a radius of 26, for a phi of 11.3 and a z of -0.4, that would put us in the plus minus octant, and so therefore we need to rotate by 180 degrees. That's a consequence of the fact that tangent of -1 over -5 is the same as tangent of 1 over 5. So when you've got 2 minus signs in the tangent, you really have to pay attention. And so because we're not in the right octant with this solution, we need to rotate this angle by 180. And so that results in a rho phi z of being equal to 26, and I'm just going to go with degrees here, comma 191.3, comma -4. So that's the conversion from Cartesian to spherical, or sorry, to it's obviously not spherical, that's cylindrical. And then if we're going to go to spherical, r is equal to x squared plus y squared plus z squared. So that's equal to the square root of -5 squared plus -1 squared plus -4 squared. So the radius of that sphere is going to be 6.5 meters. Theta is equal to the inverse cosine of z over r. And so that's cosine -1 of -4 over 6.5. And that's equal to 2.234 radians. And phi is equal to inverse tangent of y over x, which is equal to 3.39 radians. So that's an example of conversion from Cartesian to the other two coordinate systems. And here we've got a second example, convert the point 5, pi over 2, 3 pi over 5 to the other coordinate systems. So I noticed that that's a distance, that's an angle, that's an angle. That means this is a spherical point. And I'm going to give you the answers. I encourage you to do this conversion on your own. The Cartesian, the answer is x equals -1.55, y is equal to 4.76, and z is equal to 0. And in cylindrical, the answer is rho is equal to 5 meters, phi is equal to pi over 2 radians, and z is equal to 0 meters. So you can do those on your own to test your understanding of the conversions.